The cosmos hides a secret code written into its very fabric. We are about to embark on a journey through 30 of the most mind-bending theories that attempt to crack this cosmic cipher. You will gain a new lens to see the universe, one where reality might be a projection, and every choice spawns a new world. We will explore if our universe is just one bubble in an infinite foam and question whether time itself is an illusion. What single cosmic mystery keeps you up at night, wondering our reality might be nothing more than a magnificent illusion? This is the startling claim of the holographic principle, a theory suggesting the three-dimensional universe we experience is a projection from a two-dimensional surface at its cosmic edge. Think of the hologram on your credit card. It appears to have depth and volume, a three-dimensional image you could almost reach into. But that image is not truly three-dimensional. All of its information is encoded on a flat, two-dimensional piece of plastic. In the same way, physicists like Leonard Susskind and Gerard T. Hooft propose that our entire universe, with its galaxies, stars, and planets, could be a cosmic hologram. All the information needed to describe every event, every particle, and every law of physics within our three-dimensional space might be painted onto a distant, two-dimensional boundary that surrounds us. This solves a profound puzzle about black holes. When matter falls into a black hole, what happens to the information it contains? According to the holographic principle, the information is not lost inside the three-dimensional void. Instead, it is smeared and stored on the black hole's two-dimensional event horizon, the point of no return. The implications are universe-shattering. If this is true, then the world we perceive as solid and real is a kind of projection, a translation of data from a flat surface. The depth you see, the space you move through, could be a convenient and incredibly detailed illusion. Are we and everything we know just shadows on a wall? If our universe is a hologram, what triggered its initial projection? The answer may lie in an event of unimaginable violence that occurred in the first fleeting moments of existence. This is the theory of cosmic inflation. In the tiniest fraction of a second after the Big Bang, the universe did not simply expand, it exploded in size. It underwent a growth spurt so rapid and so extreme that it defies all everyday comparison. The entire cosmos we can observe today, spanning billions of light years, ballooned from a subatomic speck to a macroscopic universe in less than a blink of an eye. This incredible idea was proposed to solve two profound puzzles. The first is the horizon problem. Look at the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. No matter which direction we look, this radiation is almost exactly the same temperature. But how can two opposite sides of the universe be the same temperature if they were never in contact? They are too far apart for light or heat to have ever traveled between them, even in the universe's entire history. It is as if two strangers on opposite sides of the world started singing the same song in perfect unison without ever having met. Inflation solves this by suggesting that these distant regions were indeed once close together, nestled in that tiny primordial seed. The inflationary burst then stretched them apart faster than the speed of light, locking in that uniform temperature before they were forever separated. The second puzzle is the flatness problem. Measurements show the geometry of our universe is incredibly flat, not curved on the largest scales. For the universe to remain so flat for so long requires its initial expansion rate and density to have been fine-tuned to a precision of 1 part in a million trillion. Inflation naturally produces this flatness. Think of blowing up a balloon. A tiny, wrinkled patch on the deflated balloon becomes vast and smooth as the balloon inflates. In the same way, the violent stretching of space during inflation ironed out any initial curvature, leaving behind the flat universe we measure today. The engine for this incredible expansion is thought to be a mysterious field that permeated the early cosmos called the inflaton field. As this field shifted its energy state, it released a colossal repulsive force, driving space itself to expand at an exponential rate. The evidence for this wild theory is etched into the cosmos itself. Tiny, random quantum fluctuations in that inflattened field were stretched to astronomical sizes by inflation, becoming the seeds for all the large-scale structure we see today. Every galaxy, every star, every planet owes its existence to those microscopic ripples, magnified by the universe's most dramatic growth spurt. But if inflation stretched our universe to such an immense scale, what lies beyond the horizon we can see? The theory of cosmic inflation naturally leads to a staggering possibility, the first level of the multiverse. If space is truly infinite, then the arrangement of matter and energy cannot be unique. With an endless cosmic canvas, every possible configuration of particles must eventually repeat. This means that somewhere in the vastness beyond our observable bubble, there exists another Earth. Not just a similar planet, but an exact duplicate where a version of you is listening to this very sentence, perhaps making a slightly different choice in this exact moment. The implications are dizzying. For every historical event that unfolded one way here, there is a realm where it unfolded another. A universe where you never moved from your hometown and another where you became an astronaut. This is not science fiction, but a direct mathematical consequence of an infinite, post-inflationary cosmos. The sheer size of reality guarantees the repetition of patterns, no matter how complex. The philosophical questions are immediate and profound. What does this say about our uniqueness, our free will, if every decision branches into an infinity of pre-existing outcomes? It challenges the very notion of self. Are you the product of your singular life story, or simply one copy in an endless library of nearly identical biographies? The cosmos becomes less a single creation and more an infinite tapestry, weaving and reweaving every possible thread of existence. An infinite cosmos of identical Earths is one thing, but what if other universes are not just rearrangements of our own stuff, but are built from entirely different blueprints? This brings us to the second, even more profound level of the multiverse, a realm of bubble universes. The same mechanism of cosmic inflation that smoothed our universe never truly turned off everywhere. According to the theory of eternal inflation, the repulsive force driving that initial expansion continues to operate in a vast background meta-universe. In this eternally inflating sea, random quantum fluctuations can trigger the formation of localized pockets where inflation ends. When inflation stops in one of these pockets, that region settles down, cooling to form a stable universe with its own Big Bang, just as ours did. Each of these pockets is a separate bubble universe, forever inflating away from its neighbors in an ever-growing cosmic foam. The truly radical idea is that when a new bubble forms, the fundamental laws of physics within it can be different. The strength of gravity, the mass of an electron, the number of spatial dimensions, all of these fundamental constants could be randomly set as the bubble pinches off. In this cosmic lottery, most bubbles would be stillborn, with laws too unstable to form atoms or too violent to allow galaxies to coalesce. Our universe, with its seemingly perfect balance of forces that allow for stars, planets, and life, would be just one lucky ticket in an infinite sea of losing ones. This provides a potential answer to one of the deepest mysteries in science, the fine-tuning problem. Why do the constants of nature appear so exquisitely calibrated for our existence? If the strength of the nuclear force was slightly weaker, hydrogen would not fuse and stars would never shine. If the cosmological constant were slightly stronger, the universe would have ripped itself apart before life could begin. The bubble universe theory suggests there is no deeper reason for this perfection. We simply find ourselves in one of the rare bubbles where the numbers came out right. We are not the purpose of the cosmos, but rather the accidental inhabitants of a cosmic oasis, surrounded by an unimaginable diversity of dead and alien realities. While bubble universes offer a cosmos of different laws, there is a theory that suggests an infinite number of realities are being created right here, right now, with every possible quantum event. This is the third level of the multiverse, born not from cosmology, but from the bizarre rules of the quantum world. The story begins in the 1950s with a brilliant and unconventional graduate student named Hugh Everett. He was deeply troubled by the prevailing explanation of quantum mechanics, known as the Copenhagen interpretation. This view stated that a particle, like an electron, exists in a blurry cloud of all possible states, a superposition until it is observed. The very act of measurement, of looking at it, forces it to randomly collapse into one definite reality. Everett found this idea messy and unsatisfactory. Why should consciousness have such a privileged, magical role in shaping reality? He proposed a stunningly simple and radical alternative. He suggested that the wave function, the mathematical description of all possible states, never collapses. Instead, every single possible outcome of a quantum event actually happens. When a measurement is made, the entire universe splits into multiple branches, each one containing a different version of the outcome. Imagine you are about to flip a quantum coin. In one branch of reality, it lands heads. In another, completely separate branch, it lands tails. Both outcomes are equally real. There was no random collapse, only a deterministic branching of reality itself. You, the observer, also split. There is a version of you who sees heads and a version who sees tails, each unaware of the other's existence. This is the many worlds interpretation. Every quantum event, from the decay of a radioactive atom to the path of a photon, creates new, branching universes. Every choice you believe you are making is, in a sense, being made in every possible way across the sprawling tree of reality. This provides a breathtakingly vast multiverse, one where every possible history and future is not just out there in space, but is being written into existence at every moment. The universe becomes a constantly forking path, a tapestry of infinite parallel nows. The branching paths of the many worlds interpretation are built upon the strange rules of the quantum realm. But what if the fundamental ingredients of reality are not even particles at all? This leads us to the most ambitious and mathematically intricate attempt to decode the universe's hidden patterns, string theory. For centuries, we have thought of the most basic building blocks of nature as infinitesimal points, like tiny, zero-dimensional dots. Electrons and quarks were seen as nature's final, indivisible beads. String theory shatters this picture entirely. It proposes that at the heart of every particle is not a point, but an unimaginably small, vibrating loop or strand of energy, a string. These strings are so small that if an atom were magnified to the size of our solar system, a single string would be no larger than a tree on Earth. The theory suggests that the only difference between an electron and a quark, between a particle of light and the Higgs boson, is the way these tiny strings vibrate. Think of a violin string. It can vibrate in different modes to produce distinct musical notes, from a low C to a high G. In the same way, a fundamental string can vibrate in one pattern to create an electron, and in a different, more energetic pattern to create a photon. In this elegant vision, the entire universe is a cosmic symphony, composed by the harmonies of these vibrating strings. For this symphony to be mathematically consistent, however, the strings cannot simply vibrate in the 3 dimensions of space and 1 of time that we experience. The equations of string theory demand more room. They only work if the universe has 10 or possibly 11 spatial dimensions. This immediately raises a profound question. If there are extra dimensions, where are they hiding? The leading proposal is that these dimensions are curled up or compactified into shapes so incredibly tiny that they are completely invisible to our every perception and our most powerful instruments. The favored shapes for these hidden realms are known as Calabi-Yau manifolds. These are complex, multi-dimensional geometric forms that look like intricate 6-dimensional knots. The specific way a Calabi-Yau manifold is curled determines the vibrational patterns that are possible for the strings, which in turn dictates the laws of physics in our observable four-dimensional world. The number of particles, the forces they feel, the very nature of reality itself, could all be a consequence of the geometry of this hidden microscopic landscape. This is the ultimate promise of string theory, a single, unified framework that can describe all forces and all matter, a true theory of everything. It seeks to weave Einstein's theory of gravity, which governs the cosmos, together with quantum mechanics, which rules the subatomic world, into one seamless tapestry. Yet for all its mathematical beauty and grand ambition, string theory faces a monumental challenge. The energies required to directly observe strings or probe these extra dimensions are far beyond the reach of any particle accelerator we could ever hope to build. Without a testable prediction that can be verified or falsified by experiment, string theory remains, for now, a magnificent and powerful piece of abstract mathematics, a potential key to the cosmos with no definitive lock to try it in. String theory's elegant symphony of vibrating strings presents a puzzle of its own. For years, physicists worked not on one string theory but 5 distinct versions. Each was mathematically self-consistent, yet they all seemed to describe different facets of reality. The quest for a single, unified theory appeared to have splintered into 5 separate paths. This changed with a revolutionary leap known as M-theory. Think of those 5 string theories not as competitors, but as 5 different shadows cast by a single, unseen object. M-theory is the proposal of that true object, a master framework that unifies all 5 string theories into one coherent whole. It achieves this by adding one more dimension to the fabric of spacetime, bringing the total to 11. In this grander arena, the vibrating strings of the older theories are revealed to be just one type of object among others. The most profound new entities introduced by M-theory are called branes, short for membranes. A brane can have many dimensions. A one-dimensional brane is a string. A two-dimensional brane is a membrane, like a sheet, but branes can be much larger, stretching across multiple dimensions of space. Our entire universe, with its 3 spatial dimensions, might not be all there is. M-theory suggests we could be living on a giant, 3-dimensional brane, floating within a much larger, higher-dimensional space called the bulk. In this breathtaking picture, the stars, galaxies, and everything we know are stuck to the surface of our home brane, like dust particles trapped on a soap film. This radical idea offers a stunning explanation for one of the oldest mysteries in physics: why gravity is so unimaginably weaker than all other forces. The electromagnetic force that holds atoms together is stronger than gravity by a factor of 1 with 40 zeros after it. Why is the force that shapes the cosmos itself such a faint whisper? The brane world hypothesis provides an answer. Perhaps the particles of light and matter, like electrons and photons, are open strings whose ends are pinned to our brane. They are forced to move and interact entirely within our 3-dimensional realm. But the particle that carries the gravitational force, the graviton, could be a closed loop of string, a tiny vibrating circle with no ends to tie it down. This graviton would not be confined to our brane. It could leak away, drifting off into the higher dimensional bulk. From our perspective, trapped on our 3-dimensional sheet, the force of gravity would appear diluted, its strength seeping out into the unseen dimensions. Gravity feels weak not because it is inherently feeble, but because it is the only force that is free to explore the full volume of reality. This leads to an even more dramatic possibility. If our universe is one brane adrift in a higher dimensional ocean, there could be others. Countless other branes might be floating in the bulk, each one its own separate universe with potentially different laws of physics. And sometimes these cosmic membranes could collide. The force of such a collision would be beyond comprehension, injecting an immense amount of energy into the fabric of each brane. Could such a cataclysmic event be the origin of our own cosmos? Some physicists propose that our Big Bang was not a singular point of creation from nothing, but the aftermath of a colossal collision between our brain and a neighboring one in the bulk. The entire fiery birth of our universe, the explosive inflation and the seeding of all galaxies, might have been triggered by a shudder that echoed through a higher dimensional space we cannot even see. This cosmic lottery of bubble universes and colliding branes leads us to a profound and deeply personal question. Why do we, as conscious observers, find ourselves in a universe so perfectly suited for our existence? This is the core of the anthropic principle, a simple yet controversial idea that forces us to confront our own place in the cosmos. The principle comes in two distinct forms, one cautious and one bold. The weak anthropic principle is a statement of cosmic selection bias. It notes that we can only observe a universe that has the properties necessary for our existence as observers. In an infinite multiverse with countless universes possessing different physical constants, we obviously must find ourselves in one of the rare ones where those constants allow for stars, planets, and carbon-based life. It is like a lottery winner marveling at their luck while ignoring the millions of other tickets that lost. The fact that we are here to ponder the question automatically filters the kind of universe we are capable of seeing. The strong anthropic principle, however, takes a much more radical stance. It suggests that the universe must have those life-permitting properties, that the laws of physics are in some sense compelled to allow for the emergence of conscious life. This version often drifts into teleology, the idea that the universe has a purpose, and that purpose is us. Proponents of the strong principle point to the incredible fine-tuning of the cosmos. They ask why the cosmological constant is so precisely set to allow for galaxy formation, or why the strong nuclear force is perfectly calibrated to create the carbon atoms that are essential for life as we know it. The strong anthropic principle implies this is not a lucky accident, but a fundamental requirement of reality itself. This idea is intensely controversial within cosmology. To many scientists, the strong version sounds less like a scientific principle and more like a philosophical or even theological argument. It seems to put conscious life back at the center of the universe, a position we have been steadily abandoning since the Copernican revolution. Critics argue that it halts further inquiry, answering the question of why the universe is the way it is by simply saying it must be for us to exist. The weak version, in contrast, is widely accepted as a logical necessity. When combined with the multiverse, it provides a powerful, if humbling, explanation for fine-tuning. We are not special, and the universe was not made for us. We are simply the lucky inhabitants of one exceptionally hospitable bubble in a frothing sea of mostly dead and sterile realities. The anthropic principle, in the end, is a mirror. It reflects our deepest questions about whether our presence here is a magnificent coincidence or the point of the entire cosmic story. The idea that our universe might be a carefully crafted simulation pushes the anthropic principle to its logical extreme. If a universe must be capable of producing observers, then what if those observers eventually learn to build universes of their own? This is the core of the simulation hypothesis, a modern philosophical argument with startling scientific implications. Philosopher Nick Bostrom formalized this idea by proposing a trilemma, a set of three possibilities, one of which he argues must be true. The first possibility is that almost every civilization at our level of technological development goes extinct before it becomes capable of creating realistic simulations. The second is that even if they survive, no advanced civilization has any interest in running a vast number of simulations of their own ancestral past. The third and most provocative is that we are almost certainly living in a simulation right now. Bostrom's reasoning is based on a simple numbers game. If even one advanced civilization avoids extinction and chooses to run many such simulations for research or entertainment, the number of simulated minds would utterly dwarf the number of original biological ones. Therefore, if you are a conscious being, the statistical probability is that you are one of the simulated ones, not an original. This argument forces us to confront the nature of reality itself. Could the strange rules of quantum mechanics be evidence of this cosmic computation? The fact that matter and energy appear to be quantized, coming in discrete, indivisible packets, is reminiscent of the pixels in a digital image. The finite speed of light could be the processor speed of the universe, a limit on how quickly information can be updated across the simulation. Even the bizarre phenomenon of quantum entanglement, where particles instantly influence each other across vast distances, could be explained as a programming shortcut, two objects referencing a single piece of code in the simulation's memory. Proponents of the idea sometimes look for potential glitches in the matrix, tiny errors in the rendering of reality. These might manifest as statistical anomalies in the outcomes of particle experiments, or fleeting inconsistencies in the laws of physics that we assume are constant. The unsettling conclusion is that we may never know for sure. A sufficiently advanced simulation would be indistinguishable from base reality to its inhabitants. Your senses, your memories, and the very stars above your head could all be part of an immensely complex and convincing model, running on some post-human civilization's computer. This theory does not necessarily make our lives less meaningful, but it does reframe the very substance of existence, suggesting that at its heart, the cosmos may not be made of strings or fields, but of pure information. If reality at its most fundamental level is built from information, what is the nature of the mind that processes it? The simulation hypothesis forces a confrontation with the deepest mystery of all, the origin of consciousness itself. A radical theory suggests we have been looking at this problem backwards. Instead of consciousness emerging from the complex computation of the brain, what if it was there from the very beginning? This is the premise of panpsychism, the idea that consciousness is a fundamental and ubiquitous feature of the physical world. In this view, the capacity for some form of subjective experience is not a late arriving product of evolution, but a basic property of matter as fundamental as mass or charge. Just as an electron has a certain mass and a negative charge, it might also possess a tiny, elemental form of feeling or awareness. This does not mean an electron is thinking or has emotions. Its inner life would be unimaginably simple, a faint glimmer of experience perhaps comparable to a single note of sensation. But it is there, a building block of mind woven into the fabric of reality. Panpsychism directly challenges the standard materialist view, which holds that consciousness is an illusion generated by the sheer complexity of neural networks in the brain. Materialism has famously failed to solve what philosopher David Chalmers called the hard problem of consciousness. This is the problem of explaining how and why we have qualitative, subjective experiences. Why does the processing of visual information in the brain produce the actual, felt experience of the color red? Why is there an inner movie playing at all? We can map every neuron and every synapse, but no physical description seems capable of bridging the gap between objective brain activity and subjective feeling. Panpsychism offers a potential solution. It proposes that consciousness did not emerge from non-consciousness. Instead, the simple, proto-conscious properties of fundamental particles somehow combine and unify as those particles form more complex structures. In a human brain, the billions of neurons and trillions of connections create a system so integrated that the myriad micro-conscious experiences within it coalesce into the rich, unified stream of awareness you are experiencing right now. This idea finds a curious and highly debated resonance with quantum mechanics. The strange behavior of particles in the quantum world, where their state seems dependent on observation, has led some physicists to speculate about a link between consciousness and the quantum realm. Could the collapse of the wave function, the moment a probability becomes a definite reality, be tied to an act of observation by a conscious system? Panpsychism provides a framework where consciousness is already present in the system, potentially playing a role in this fundamental process. The theory does not claim that a rock is conscious in the way we are, because its atomic constituents are not integrated into a unified whole. But it does suggest that the ingredients for consciousness are present everywhere in everything. This perspective transforms our place in the cosmos. We are not strangers in a dead, mechanical universe suddenly waking up. We are the universe itself, becoming gradually more aware, discovering its own existence through us. Every thought you have might be the cosmos thinking, a local concentration of a fundamental property that has been here all along. But if consciousness is a fundamental property of the cosmos, can it exist independently of the physical structures we recognize? This question leads to one of the most unsettling thought experiments in all of physics, the Boltzmann brain paradox. It begins with a simple, undeniable fact. The universe is overwhelmingly chaotic and disordered, a state physicists call high entropy. Yet here we are in a pocket of astonishing order, with structured planets, living organisms, and conscious minds. How did such a low entropy state come to be? In an eternally existing universe, the most likely outcome is not a vast, ordered cosmos, but random, fleeting fluctuations out of the chaos. Given enough time, the random jostling of particles in the void could, by sheer chance, assemble anything. It is far more probable for this randomness to spontaneously form a single, self-aware brain, complete with false memories of a past that never happened, than it is to form an entire, orderly universe that evolves over billions of years. This hypothetical entity is a Boltzmann brain. It would pop into existence for a mere moment, convinced it is a person living in a real world, before dissolving back into the formless vacuum. The paradox is terrifying in its implications. If our cosmological models point toward an eternal, evolving universe, then the statistical probability is that you are one of these momentary, disembodied brains, and the entire universe you remember is a complete fabrication. Your childhood, the stars in the sky, every single piece of evidence you have for a consistent reality, would be nothing more than an elaborate and convincing illusion generated by a random accident. This is not just a philosophical puzzle. It strikes at the heart of cosmology's attempt to explain the arrow of time, the reason we remember the past but not the future. Our sense of a linear, flowing time depends entirely on the universe starting in an incredibly ordered, low-entropy state. The Boltzmann brain paradox suggests that in an eternal cosmos, our memories and the arrow of time we experience are fundamentally unreliable. It forces physicists to confront a stark choice. Either our current understanding of the universe's history and future is profoundly wrong, or we must accept that we are almost certainly not who and what we think we are. The search for a cosmology that naturally produces a universe like ours, without making disembodied phantom minds the most likely observers, remains one of the most pressing challenges in modern physics. The terrifying prospect of being a fleeting Boltzmann brain forces us to reconsider the ultimate fate of our cosmos. What if the universe is not a one-time event destined for cold emptiness, but part of an endless, repeating cycle? This is the cyclic model of the universe, a vision where the cosmos has no true beginning and no final end. Instead, it undergoes an eternal rhythm of death and rebirth. In this picture, our Big Bang was not the absolute start of everything, but merely the latest in an infinite series of cosmic explosions. Each cycle begins with a hot, dense state that expands and cools, giving rise to galaxies, stars, and life, just as our universe has. But instead of expanding forever into a dark, thin void, the expansion eventually slows, halts, and reverses. All matter and energy are pulled back together in a cataclysmic event known as the Big Crunch. Imagine the entire history of the universe, every star and every galaxy, collapsing inward as if rewinding a film of cosmic expansion. the universe contracts into an incredibly hot, dense state, erasing all structure and effectively hitting a cosmic reset button. This dense state then triggers the next Big Bang, launching a new cycle of expansion and creation. This elegant idea provides a beautiful solution to the entropy problem that plagues the Boltzmann brane paradox. In a single, linear universe, entropy or disorder only increases, making a highly ordered beginning a profound mystery. But in a cyclic universe, the intense heat and compression of each big crunch effectively smooths everything out, resetting the entropy to a low, ordered state for the next cycle. The universe gets a fresh start each time, wiping the slate clean so that new galaxies and new life can form again. One of the most developed versions of this idea is ekpyrotic cosmology, a theory born from string and M theory. It proposes that our Big Bang was not a singularity from nothing, but the result of a collision between two branes in a higher dimensional bulk. In this model, the cycles are driven by the slow, rhythmic motion of these parallel worlds. The branes periodically attract each other, drawing closer until they collide. That collision releases an immense firestorm of energy, which we experience as our Big Bang. The branes then bounce apart, the universe expands and cools on their surfaces, and the gravitational attraction between them slowly pulls them back together over trillions of years, setting the stage for the next collision and the next cosmic cycle. This process could have been repeating for all eternity, with no first cause and no ultimate end. The cyclic model offers a profoundly different perspective on our place in the grand scheme. We are not living in the first and only universe, but in one iteration of an infinite cosmic recurrence. Every constellation in our sky, every planet, and every conscious mind has likely existed in similar forms countless times before, and will do so again forever. It is a vision of the cosmos as a timeless, self-sustaining engine of creation, where death is always followed by rebirth on the grandest possible scale. The cyclic model finds its most profound expression in a theory that redefines infinity itself. Roger Penrose's conformal cyclic cosmology proposes a universe without a true beginning or end, but not through a violent crunch and rebound. Instead, it envisions an endless procession of eons, each one a complete universe epoch, where the unimaginably distant future of one seamlessly becomes the hot, dense Big Bang of the next. The key to this elegant transition lies in a process called conformal rescaling. As a universe expands toward its final state, all that remains is an ever-thinning sea of radiation and evaporating black holes. Particles lose their mass, distances become meaningless, and the vast, cold, empty cosmos effectively forgets its scale. In this featureless state, the end of time in one eon is geometrically identical to the explosive beginning of the next. The infinite becomes the infinitesimal, and a new Big Bang ignites from the ashes of its predecessor. This is not a collision or a bounce, but a smooth, mathematical transformation of the end into a new beginning. But if universes have come before ours, could they have left a mark? Penrose and his collaborators believe they have found the evidence etched into the oldest light we can see. They argue that the cosmic microwave background, the afterglow of our own Big Bang, should contain faint circular imprints called Hawking points. These are theorized to be the final, explosive bursts of energy from supermassive black holes that evaporated in the previous eon. In the final moments of that prior universe, as black holes dissolved through Hawking radiation, they would have released colossal amounts of energy. When that eon transformed into our Big Bang, those immense flashes would have been imprinted as subtle, ring-like temperature variations on the very first wall of our new cosmos. Finding these faint circles in the microwave sky would be like discovering fossils from a universe that died trillions upon trillions of years before our own was even born. The existence of such a pattern would be a direct window through the veil of a single Big Bang, revealing an eternal, cyclical cosmos where death is merely a prelude to an infinite number of new beginnings. The smooth, eternal cycles of conformal cosmology present a universe where time is a vast, repeating loop. Yet our own lived experience feels nothing like a loop. It feels like a relentless, one-way flow from the past into the future. This deep-seated intuition about time, however, might be the universe's greatest trick. Special relativity, one of the most thoroughly tested theories in all of physics, paints a picture of reality so radical it shatters the notion of a flowing present entirely. This is the block universe theory, also known as eternalism. In this view, the past, present, and future are not sequential. They all exist simultaneously, fixed forever in a single, four-dimensional structure. We can think of this structure as a cosmic loaf of bread. Each slice of that loaf represents the entire universe at a single moment in time. The first slice is the Big Bang. A slice in the middle holds dinosaurs roaming the earth. Another slice contains you, listening to this sentence right now. And a slice far down the loaf holds every event we would consider the distant future. In the block universe, all of these slices are equally real. They all exist. The feeling that time is passing is just an illusion of our consciousness, a mental cursor moving from one static slice to the next within the eternal block. This idea emerges directly from Einstein's equations. Relativity tells us that there is no universal now. What is the present for you depends on how you are moving through space. If one person is on a high-speed rocket ship and another is on Earth, they will not agree on which events are happening simultaneously. Your present could be someone else's past and another observer's future. Since there is no privileged, universal present moment, it makes no sense for physics to single out one slice of time as the real one and dismiss the others as unreal or non-existent. The flow of time is a stubborn, powerful illusion, like the feeling that the landscape is moving when you are sitting on a stationary train and another train passes by your window. The landscape of space-time is static. We are the ones moving through it. This has immediate and profound consequences for our understanding of free will. If the future already exists, carved into the cosmic block just as definitively as the past, then are our choices truly free. It feels like we are making decisions that shape an open, undetermined future. But the block universe suggests that the future is just as fixed and unchangeable as yesterday's weather. Your entire life, from your first breath to your last, is already out there, a completed story. This does not mean you are a puppet blindly following a script. Your thoughts, your deliberations, your conscious experience of weighing options are all real parts of the block. They are the process by which your personal timeline unfolds within the fixed structure. You are not a spectator of a predetermined film. You are an integral part of the film itself, living out your role with genuine feeling and intention, even if the entire script is already written. The block universe does not rob life of meaning, but it fundamentally reframes what meaning is. Your life is not a fleeting spark in the darkness. It is an eternal, unchanging sculpture in the grand museum of space-time, a unique and permanent thread in the fabric of a reality where everything that ever was or will be simply is. This strange merging of quantum mechanics and personal fate leads to one of the most unsettling ideas in all of physics. Quantum immortality is a thought experiment that suggests you, as a conscious observer, might never experience your own death. This is not a promise of eternal life in a single world, but a bizarre consequence of the many worlds interpretation. Imagine a modified version of the famous Schrödinger's cat experiment, but this time you are the cat. You are placed in a box with a diabolical device. At the heart of the device is a single radioactive atom. If the atom decays, it triggers a mechanism that releases a lethal poison. If it does not decay, you walk out unharmed. According to the Copenhagen interpretation, after 1 minute, the atom exists in a superposition of both decayed and not decayed states. When you open the box, the wave function collapses, and you either find yourself alive or dead at random. But in the many worlds view, the universe splits at the moment of the quantum decision. In one branch, the atom decays and you die. In the other branch, the atom does not decay and you survive. From your subjective perspective, which outcome do you experience? You can only experience the branches where a conscious you exists to have an experience. You will always find yourself opening the box, alive and well, no matter how many times the experiment is repeated. In the branches where you die, there is no one there to observe that outcome. Your conscious awareness simply follows the path of continuous existence, hopping from one timeline to the next, forever avoiding the terminal conclusion. This logic can be extended to any life-threatening situation. A fatal car crash, a terminal illness, even old age. For every possible quantum event that could lead to your death, there is a branch universe where a quantum fluctuation, no matter how improbable, allows you to survive. You would subjectively experience a sequence of increasingly unlikely escapes, a life that seems charmed against all odds, while countless versions of you in parallel branches meet their end. The philosophical implications are deeply disturbing. It challenges the very core of our identity. Are you the same person if you survive a crash due to a 1 in a billion quantum roll of the dice? Your memories and body might be identical, but the history of your world has diverged in a fundamental way. This thought experiment also leads to a terrifying ultimate conclusion. As the universe ages over billions of years, the branches where you continue to exist become vanishingly rare and strange. You might eventually find yourself as the last conscious being in a cold, dead universe, kept alive by a continuous, miraculous sequence of quantum accidents, utterly alone for eternity. Quantum immortality is not a theory anyone can prove, as you cannot report back from the branches where you cease to be. It stands as a stark reminder that in a multiverse of infinite possibilities, the line between a statistical miracle and a subjective certainty becomes dangerously blurred. The unsettling idea of quantum immortality confronts us with the fragility of existence, but another paradox suggests that existence itself might be fundamentally indestructible. Deep within the heart of a black hole lies a conflict that has divided physicists for decades, a battle over whether information can ever truly be lost. This is the black hole information paradox. According to Einstein's general relativity, when something falls into a black hole, it passes the event horizon and is crushed into the central singularity, disappearing from our universe forever. Every detail about that object, its composition, its history, its very identity, is seemingly erased. Yet quantum mechanics, the rules governing the subatomic world, holds a sacred law. Information cannot be destroyed. It can be scrambled, hidden, or transformed, but it must be preserved. If you were to burn a book, the information within it is not gone. In principle, if you could collect every single photon of light, every particle of smoke and ash, and reverse the process with perfect precision, you could reconstruct the book. Quantum mechanics insists the universe is similarly deterministic. The destruction of information would violate this core principle, rendering the future unpredictable even in theory. For decades, it seemed general relativity won the argument within a black hole. Then Stephen Hawking made a stunning discovery: black holes are not completely black. Due to weird quantum effects near the event horizon, they slowly emit a faint glow of particles, now known as Hawking radiation. This radiation carries energy away from the black hole, causing it to gradually shrink and over eons evaporate completely. Here was the paradox in its final form. If a black hole forms from a specific collection of stars and planets, that matter carries information. The Hawking radiation that the black hole emits, however, is purely thermal and random. It contains no information about what fell in, so when the black hole vanishes, what happened to all that information? It appears to have been permanently erased from reality, violating quantum law. This was Hawking's original bet, that information was indeed lost. The physics community was thrown into chaos. A solution began to emerge from the work of Leonard Susskind and others, building on the holographic principle. They argued that the information is not lost inside the black hole. Instead, it is encoded on the black hole's two-dimensional event horizon like a cosmic fingerprint. As the black hole evaporates via Hawking radiation, this information is slowly and chaotically released back into the universe, imprinted onto the escaping radiation. The process is incredibly complex, but the information is, in principle, recoverable. This idea resolved the paradox for many, but it raised a new and bizarre question. If the information is on the surface, what happens to the three-dimensional objects that fell in? Recent breakthroughs have come from the concept of entanglement. The Hawking radiation particles are entangled with the black hole's interior. But as the black hole evaporates, this creates a problem with the original information. The solution, shockingly, involves regions called quantum extremal islands. These are not physical islands in space, but regions inside the old black hole that, through the weirdness of quantum entanglement, become part of the external space from which the information can be decoded. It is as if a piece of the interior momentarily belongs to the outside, safeguarding the information until it can be radiated away. This ties directly into another profound idea, the ER equals EPR conjecture. It proposes that two entangled particles are not just mysteriously connected, they are actually linked by a microscopic wormhole or Einstein-Rosen bridge. In the context of a black hole, this suggests that the information falling into the interior might be connected to the information on the horizon via a vast network of these tiny bridges. The interior and the surface are not separate places, they are one and the same, woven together by the fabric of spacetime itself. The information was never in danger, it was just stored in a way we are only beginning to understand. The event horizon is not a wall of no return, but a dynamic, vibrating membrane that holds the key to preserving the history of everything it has ever consumed. The profound silence of the cosmos is itself a deafening mystery. With hundreds of billions of stars in our galaxy alone, many older than our Sun and likely hosting Earth-like planets, the universe should be teeming with life. So where is everybody? This is the Fermi paradox, the stark contradiction between the high probability of alien civilizations and the utter lack of any evidence for them. One compelling and deeply unsettling solution is the Great Filter hypothesis. This theory suggests that the evolution of life from its origins to a spacefaring, galaxy-colonizing civilization requires passing through a series of incredibly difficult steps. At least one of these steps must be almost impossibly hard, a barrier so effective that it filters out virtually every species that attempts the climb. The terrifying question is whether this great filter lies in our past or waits for us in the future. If the filter is behind us, we are the rare, lucky survivors of a cosmic bottleneck. Perhaps the jump from simple prokaryotic cells to complex eukaryotic life, a transition that took over 1 billion years on Earth, is the monumental hurdle. Or maybe the development of genuine intelligence and technology is the true fluke. In this optimistic scenario, the galaxy could be filled with microbial life and simple animals, but we are among the first, or even the only, species to have made the leap to consciousness and tool use. The silence would then be a sign of our profound rarity and preciousness. The alternative is far more grim. What if the great filter is still ahead of us? This is the possibility that keeps astronomers and philosophers awake at night. Perhaps every advancing civilization eventually reaches a technological level where it inevitably discovers the means of its own destruction. This could be a nuclear apocalypse, a bioengineered plague, a runaway climate catastrophe, or an artificial intelligence that turns against its creators. The filter could even be something we have not yet conceived, a fundamental danger inherent in the structure of reality that becomes apparent only at a certain stage of development. In this view, the silence of the stars is a graveyard, a warning that no one makes it through the final challenge. We look up at an empty galaxy not because we are first, but because we are late to a party where every other guest has already perished. The Great Filter forces us to confront our own trajectory. Every breakthrough in artificial intelligence, every new energy source, every step toward becoming a multi-planetary species could be seen as both an achievement and a potential step closer to our own filter. Are we the exception that slipped through a cosmic sieve, or are we simply unaware of the wall we are about to hit? The answer to this paradox will define not only our understanding of the universe, but the ultimate fate of humanity itself. The silence of the cosmos might point to a filter we cannot yet see, but a deeper silence surrounds the very substance of the universe. We look up at the night sky and see stars and galaxies, but this luminous matter is only a tiny fraction of what is actually there. The rest is an invisible presence, a ghost in the cosmic machinery known as dark matter. Its existence was first forced upon us by the way galaxies spin. According to the laws of gravity, stars on the outer edges of a spinning galaxy should move much more slowly than those near the center, just as Pluto orbits the Sun far more sluggishly than Mercury. Yet when astronomers like Vera Rubin measured the rotation speeds of galaxies, they found something astonishing. The stars on the outskirts were moving just as fast as those near the core. It was as if the entire galaxy was embedded in a vast, invisible sphere of mass, a halo whose gravity was whipping the outer stars around at impossible speeds. Without this dark halo, galaxies would simply fly apart. The evidence does not stop there. We can also see dark matter through its gravitational lens. According to Einstein, massive objects warp the fabric of spacetime, bending the path of light that travels past them. Sometimes we see distant galaxies stretched and distorted into strange arcs and rings. The amount of bending is far too great to be caused by the visible matter alone. An immense, unseen mass must be there, acting as a cosmic magnifying glass, and we are staring right through it. This dark matter is not merely a passive backdrop, it is the primary architect of the universe's large-scale structure. After the Big Bang, it was the gravitational pull of dark matter that created the first scaffolds upon which ordinary gas could accumulate, eventually collapsing into the stars and galaxies we see today. The entire cosmic web, that vast filamentary network of galaxies stretching across billions of light years, was woven first by the invisible hands of dark matter. But what is it made of? The leading candidate for decades has been WIMPs, or weakly interacting massive particles. These are theoretical particles that are heavy, like atomic nuclei, but which barely interact with normal matter or light. They would pass through our planet and through you as if they were not even there, their presence betrayed only by their collective gravitational shadow. Despite decades of searching with incredibly sensitive detectors buried deep underground, we have not yet definitively caught one. Another compelling candidate is the action, a particle that is trillions of times lighter than an electron. Actions were originally proposed to solve a different puzzle in particle physics, but they could also make up dark matter. Because they are so light, they would exist in unimaginable numbers, a ghostly quantum wave flowing through the cosmos. Yet there is a more radical possibility. What if we have been misinterpreting the evidence all along? A minority of physicists propose that dark matter does not exist at all. Instead, they suggest our theory of gravity itself is incomplete. This idea is called MOND, or modified Newtonian dynamics. It posits that the laws of gravity change on the immense scales of galaxies, producing the extra pull we attribute to dark matter. While MOND can explain some galactic rotation curves, it struggles to account for the bullet cluster where two galaxies have collided. Observations show that the visible matter was slowed by the collision, but the gravitational lensing effect, the true mark of mass, continued on ahead, completely separated from the stars. This suggests a cloud of dark matter passed right through the collision, something MOND cannot easily explain. So the hunt continues for a particle we cannot see, or for a new law of physics that rewrites our understanding of gravity. The mystery of dark matter is a humbling reminder that most of the universe is made of something we do not understand, a hidden pattern holding the light together. While dark matter sculpts the cosmic architecture, a far more mysterious force is controlling the destiny of the entire stage. In the late 1990s, two independent teams of astronomers made a discovery that shattered the fundamental expectation for the universe's future. They were measuring the distances to extremely far-off supernova, using them as cosmic mile markers to gauge how quickly the universe has been expanding over time. Everyone expected to find that the gravitational pull of all the matter in the cosmos was slowing the expansion down, like a ball thrown upward, gradually losing speed to Earth's gravity. The results were the exact opposite. The distant supernova were fainter than they should have been, meaning they were farther away than anyone had predicted. The expansion of the universe is not slowing down, it is speeding up. This was the equivalent of throwing that ball into the air and watching it blast away faster and faster, defying gravity itself. The universe is being pushed apart by a repulsive force, an anti-gravity that permeates the vacuum of space. We call this mysterious presence dark energy. The leading candidate for dark energy is the cosmological constant, a concept Einstein originally introduced and then later called his greatest blunder. This is an energy inherent to the fabric of space itself. Empty space is not truly empty according to quantum physics. It is a seething foam of virtual particles that constantly pop in and out of existence. This quantum jitter endows every cubic centimeter of vacuum with a tiny, constant energy. While this energy is minuscule on human scales, when you add it up across the vast, empty volumes between galaxies, it becomes the dominant force in the cosmos, producing a relentless pressure that drives galaxies apart. Another possibility is that dark energy is not a constant, but a dynamic field that changes over time, known as quintessence. Imagine a new, unseen kind of fluid that fills space, one with a negative pressure. Unlike matter or radiation, whose density decreases as the universe expands, this quintessence field could become stronger, making the acceleration more potent as time goes on. The ultimate fate of our universe hinges entirely on the true nature of this dark energy. If it is a constant cosmological constant, then the acceleration will continue at a steady rate. Galaxies will be pushed apart faster and faster until all the stars in the night sky beyond our local group have vanished over the cosmic horizon. The universe will become a much lonelier place, with island galaxies drifting in an ever colder, darker, and more empty void. This is the Big Freeze, a slow heat death where the cosmos expands into eternal silence and cold. But if dark energy is a form of quintessence that grows in strength, the outcome is far more violent. In this scenario, the repulsive force becomes infinite. It would not just push galaxies apart, it would eventually overcome all the forces that hold things together. First, the gravitational bonds between galaxy clusters would be torn. Then, individual galaxies would be ripped apart. As the acceleration intensifies, stars would be shredded from their planetary systems. In the final moments, the very fabric of space-time would be torn asunder. The relentless dark energy would overcome the nuclear forces holding atoms together, and then the electromagnetic forces binding molecules. In a final, catastrophic event known as the Big Rip, every single atom, every fundamental particle, would be eternally isolated from every other in a universe that has been utterly disemboweled. There is a third, more cyclical possibility, the Big Crunch, where the acceleration eventually reverses and the universe collapses back on itself. But all current evidence points toward an accelerating fate, a cosmos being driven apart by a ghost in the vacuum. The greatest structures in the universe are not being built by gravity, but are being relentlessly dismantled by a force we cannot see or touch, a silent, enigmatic driver steering the cosmos toward an increasingly dark and lonely future. A strange and unsettling pattern is written across the oldest light in the universe. The cosmic microwave background, that faint afterglow of the Big Bang, is supposed to be a nearly perfect snapshot of infant cosmos, a random and isotropic sea of minute temperature variations. Yet when scientists created a detailed map of this radiation, they found something that should not be there, a mysterious alignment that has been dubbed the axis of evil. This axis is not a physical structure, but a preferred direction in space, a kind of cosmic tilt along which many of the largest fluctuations in the microwave background seem to be strangely coordinated. It is as if the universe has a faint but undeniable fingerprint, a whisper of order in what should be pure chaos. This discovery directly challenges one of the most cherished principles of modern cosmology, the cosmological principle. This principle states that the universe on the largest scales is homogeneous and isotropic. It should look the same in every direction, with no special places and no preferred axis. The axis of evil suggests that on the very largest scales we can observe, the universe might not be perfectly uniform after all. So what could be causing this cosmic oddity? The most conservative explanation is that it is simply a statistical fluke, a grand cosmic illusion. When you look at any random data set, you will sometimes find patterns that appear significant purely by chance. Perhaps we are just the unlucky observers in a universe that happens to have a quirky alignment in our particular patch of the sky. If we could step outside our observable bubble, this axis might vanish into a larger, truly random background. Others have proposed a more local cause, that this alignment is not a feature of the universe itself, but an artifact of our own motion. Our solar system is hurtling through space, and this movement can create a Doppler-like effect in the microwave background, a kind of cosmic wind that might imprint a false pattern onto the data. Yet when astronomers carefully correct for this motion, the axis of evil stubbornly remains. This has led to the most thrilling possibility that the axis is a genuine signal of new physics. It could be a relic from the very first moments of the universe, a scar from a time before inflation, when the fabric of space-time was fundamentally different. Perhaps our cosmos is not perfectly smooth, but has a slight rotational preference woven into its foundation, a twist in the geometry of reality left over from its birth. Or it could be evidence that our universe is not alone, that its structure was subtly influenced by a neighboring cosmos in the vast multiversal foam. The axis of evil remains one of cosmology's most persistent and controversial anomalies, a ghost in the machine that refuses to be explained away. It stands as a humbling reminder that our most fundamental assumptions about the cosmos may still be incomplete, and that the universe might yet hold a deeper, more intricate design than we have ever dreamed. That mysterious 72-second burst of radio waves known as the WOW signal remains one of the most tantalizing hints that we might not be alone. Detected in 1977 by an Ohio radio telescope, its intensity and narrow frequency band were exactly what astronomers predicted for an artificial interstellar transmission. And then it vanished, never to be heard again. Whether it was a cosmic flare, a human signal reflected off space debris, or a genuine message from the stars, it forces a profound question. If life is out there, how did it begin, not just on one world, but potentially on many? This leads to a radical theory for life's origins, one that suggests we are all citizens of a much larger cosmic ecosystem. The idea is panspermia, the concept that life's basic building blocks, or even dormant microorganisms, can travel between planets and star systems, hitchhiking on comets and asteroids. Imagine a life-bearing rock blasted from the surface of Mars by a powerful asteroid impact. Some of that debris could escape the planet's gravity, drifting through the solar system for millions of years. A tiny fraction of those Martian meteorites might eventually collide with a welcoming world like Earth, seeding it with microbial life. we have evidence that this interplanetary travel is possible. We have found meteorites on Earth that were conclusively identified as pieces of Mars, and within some of them we have discovered organic molecules, the fundamental ingredients for life. While this does not prove life itself made the journey, it demonstrates that the raw materials can survive the violent launch, the harsh radiation of space, and the fiery descent through an atmosphere. The theory gains further support from the discovery of extremophiles, incredibly resilient microorganisms on Earth that thrive in conditions once thought to be utterly sterile. Scientists have found bacteria living in boiling hot acid, in the crushing pressures of the deep ocean, and even frozen deep within Antarctic ice. If such hardy life can exist on Earth, is it so difficult to believe that a similar microbe could lie dormant inside a protective rock, surviving an interstellar voyage that lasts for eons? This vision transforms our picture of the galaxy. Instead of life sparking independently on isolated islands, it could be a single, interconnected phenomenon. A single life-bearing world in a distant star system, struck by a comet, could scatter its biological heritage across dozens of nearby stars. Life would not be a series of miraculous accidents, but a cosmic contagion, spreading slowly but surely from one stellar oasis to the next. In this light, the wow signal takes on a new meaning. It might not have been a carefully crafted hello, but an unintentional byproduct of a civilization that itself was a product of this grand galactic seeding. We and any other intelligence out there may not be independent creations, but long-lost cousins in a vast, ancient family tree whose roots are written in the dust of comets and the ice of interstellar space. Perhaps the silence from the stars is not a sign of our loneliness, but a deliberate and profound choice made by others. The zoo hypothesis offers one of the most elegant and unsettling solutions to the Fermi paradox. It proposes that advanced extraterrestrial civilizations are fully aware of our existence, but have chosen to place Earth under a kind of cosmic quarantine, observing us from a distance without ever revealing themselves. In this scenario, our planet is a designated wildlife preserve, and humanity is the species under study. The rules of this galactic society would strictly forbid any form of contact, ensuring that our cultural and technological development remains entirely uncontaminated by outside influence. They want to see what we become on our own, just as a naturalist would never step into a fragile ecosystem to guide its evolution. The motivations for such a policy could be profoundly ethical. A civilization that has survived its own technological adolescence would understand all too well the dangers of sudden, disruptive contact. The historical record on our own world is a grim lesson in what happens when an advanced culture encounters a less technologically developed one, often leading to exploitation, disease, and cultural collapse. A truly enlightened galactic community might have a prime directive of non-interference, a universal law designed to protect emerging civilizations like ours from being overwhelmed before we are ready. The sociological implications are staggering. Every unexplained UFO sighting, every strange signal that fades before it can be verified, could be brushed off as a mere glitch. But what if they are the subtle, occasional slips of an otherwise perfect observational apparatus? How would our society change if we knew for certain that we were being watched? Would it fuel paranoia or inspire a new global unity as we strive to present our best face to the unseen audience? The zoo hypothesis reframes our entire search for meaning. Our drive to explore the cosmos and find our place in it might be the very behavior our silent watchers are most interested in documenting. Our greatest achievements in art, science, and compassion, as well as our deepest failures in war and environmental neglect, all become data points in a grand galactic anthropological study. The question is no longer where everybody is, but what we must do to eventually graduate from the zoo and earn an invitation to join the galactic conversation. The silent observation of a cosmic zoo depends on a reality we all agree upon, but what if that shared reality is not a given? It is a fragile consensus built one photon at a time. Quantum Darwinism tackles the greatest mystery left by the quantum world, the transition from its blurry realm of possibilities to the solid, objective world we see around us. Why does a table appear to be in one definite place to everyone who looks at it, while an electron exists in a haze of potential locations until measured? The answer may lie not in a magical act of observation, but in a process of natural selection for information. Think of a quantum system like a newly emitted photon. It is in a superposition, a mixture of all possible states, such as vibrating both horizontally and vertically at once. This fragile state cannot withstand contact with the environment. The moment it interacts with even a single air molecule, countless copies of information about its state are imprinted onto that molecule, and then onto others, and then onto trillions more. This is the essence of quantum Darwinism. The states that are most robust, the ones that can be copied and spread most efficiently into the surrounding environment, are the ones that survive. They are the fittest quantum states. These proliferating imprints become the consensus reality. When you walk into a room and see a chair in the corner, you are not directly perceiving the chair itself. You are intercepting a tiny fraction of the countless photons that have scattered off the chair, each one carrying a redundant copy of the information that the chair is, in fact, in the corner. Your brain is not collapsing a wave function. It is simply reading from a cosmic bulletin board that has been plastered with the same message over and over again by the environment. The reason we all agree on the chair's location is that we are all sampling from the same widely distributed set of data. This process explains why we never see macroscopic objects in superpositions. A cat cannot be both alive and dead because its state is constantly being monitored and recorded by the trillions upon trillions of air molecules, dust particles, and photons bouncing off it. The information about its aliveness or deadness is copied so many times so quickly that the superposition has no time to exist. It is stabilized into a single classical reality through a blizzard of environmental interaction. Quantum Darwinism provides a mechanism for how objective reality emerges without needing a conscious observer. The environment is the observer, a relentless, impartial scribe that records the history of the universe in a language of scattered particles. What we perceive as the solid, dependable world is simply the winning ticket in a continuous lottery of quantum possibilities. Its number broadcast so widely that we all mistake it for the only reality that ever was. The ghostly presence of dark matter could be hiding in the most ancient and violent relics of creation. For decades, physicists have searched for exotic new particles, but what if the answer is not a tiny WIMP or an action, but a vast population of cosmic fossils from the universe's first second? This is the theory of primordial black holes. Unlike the stellar black holes formed from collapsing stars, these would have been forged in the extreme density and pressure of the Big Bang's immediate aftermath. Tiny fluctuations in the newborn cosmos could have caused regions of space to collapse directly under their own gravity, pinching off into black holes of almost any size. They could be as small as an asteroid or as massive as 1,000 suns, a hidden archipelago of dark objects woven throughout the galaxy. The beauty of this idea is its simplicity. It requires no new particles beyond the standard model, only the known laws of gravity operating in the seething cauldron of the early universe. These primordial black holes would be the perfect dark matter candidate. They do not emit or reflect light, they interact only through gravity, and they would naturally cluster in the vast halos surrounding galaxies, exactly as the dark matter does. So how could we ever detect these invisible ghosts? One of the most promising methods is gravitational microlensing. Imagine a primordial black hole drifting through space in the vast halo of our galaxy. If it passes directly between Earth and a distant background star, its gravity will act as a lens, bending and focusing the star's light. From our perspective, the star will temporarily appear to brighten, then fade, as the black hole's invisible mass moves across our line of sight. Astronomers have conducted these microlensing surveys, and they have found a puzzling result. There are not enough of these small, planet-sized lenses to account for all the dark matter, but there is a window of possibility for black holes in a specific mass range. The renewed interest in this theory comes from a completely different direction: the detection of gravitational waves. When the LIGO Observatory recorded the first ripples in space-time from colliding black holes, it revealed a surprise. The black holes involved were far more massive than anyone expected from standard stellar collapse. Their unusual heft is perfectly consistent with them being primordial, ancient relics from the dawn of time. Could the cosmic dark matter halo be filled with these primordial pairs, slowly spiraling together over billions of years? The hunt is now on for their unique signatures, from the subtle flickering of distant quasars to the precise patterns they would imprint on the cosmic microwave background. If confirmed, it would mean that the invisible skeleton of the cosmos is built from the oldest and most enigmatic objects in existence. This cosmic cycle of collisions provides an elegant alternative to the theory of inflation. The ekpyrotic universe model suggests our Big Bang was not a singular point of creation, but the aftermath of a titanic impact in a higher dimensional reality. Picture our three-dimensional universe as a vast, flexible membrane or brane, floating within a hidden fourth spatial dimension. Nearby, another three-dimensional brane drifts in this unseen bulk. The two are drawn together by a force, perhaps gravity, moving slowly and almost in parallel. When they finally collide, the energy of that impact is cataclysmic. It is this violent meeting that ignites the hot, dense state we recognize as the beginning of our cosmic timeline, instantly filling our brain with radiation and matter and setting it expanding. This is not a one-time event. The branes bounce apart, expand and cool, and are then gravitationally pulled back for another collision, creating an endless, rhythmic cycle of cosmic death and rebirth. This elegant dance of colliding worlds solves the same cosmological puzzles that inflation was designed to answer, but through a completely different mechanism. The horizon problem, the mystery of why the universe has a uniform temperature in all directions, is resolved by the pre-collision state. Before the bang, the two branes were in a long, slow, and uniform interaction across their entire surfaces. This period of gentle contact allowed energy to be evenly distributed throughout the entire structure. The collision then happened everywhere at once, imprinting that initial uniformity onto the newborn universe, ensuring that its starting temperature was the same in every region. The flatness problem is also naturally explained. The attractive force between the branes acts to smooth out any initial wrinkles or curvature over the long cycles. Just as two sheets of glass pressed together will expel air bubbles and become perfectly parallel, the drawn-out interaction between the branes flattens them, ensuring that the universe born from their collision inherits this precise flat geometry. This model paints a breathtaking picture of reality, where our entire cosmic history is just one chapter in an infinite epic of colliding worlds, a universe with no ultimate beginning and no final end. The physics of a black hole's interior inverts our understanding of reality. According to general relativity, once you cross the event horizon, space and time swap their fundamental roles. The direction toward the singularity is no longer a place you can avoid, it becomes your future. Time itself flows inexorably toward that final point of infinite density. Now consider the beginning of our own universe, a state of seemingly infinite density and temperature we call the Big Bang. The equations that describe a collapsing star into a black hole and an expanding universe from a hot, dense state are strikingly, eerily similar. This mirroring of mathematics has led some physicists to a breathtaking speculation. What if our entire cosmos is the interior of a black hole existing in a larger parent universe? In this view, our Big Bang was not the absolute beginning of everything, but the moment of formation for our event horizon as seen from the outside. When a massive star collapses in the external universe, it culminates in a singularity. But what if that singularity, from our perspective inside, is not a point of destruction, but the explosive start of everything we know? The immense energy and matter that burst forth to create our galaxies could be the transformed remains of the star that collapsed, its material reborn into a new cosmic landscape. This idea offers a profound connection between the largest and smallest scales of existence. The event horizon of our universe would be the ultimate cosmic horizon, the limit of what we can ever see. The black holes that form within our own cosmos could then themselves be entire new universes, budding off into their own dimensions of space and time. Our reality becomes a cosmic Russian nesting doll, with universes embedded within universes, each with its own unique physical laws born from the specific conditions of its parent black hole. This could provide a stunning explanation for why the constants of nature in our universe seem so finely tuned for life. Only those black holes that have the right parameters to produce a stable, long-lived interior would contain observers like us to ponder the question. We exist in a universe that is hospitable because it is one of the successful offspring in a grand trans-cosmic lineage. While this remains a highly speculative and unproven idea, it paints a majestic and humbling picture of reality, where every black hole in our sky might not be an end, but a gateway to a new beginning. Our exploration of reality has revealed universes within black holes and a cosmos reborn from cosmic collisions. But what if the fabric of time itself holds a strange new form of matter, one that moves without ever consuming energy? This is the bizarre world of time crystals. Unlike any other state of matter, from solid ice to gaseous vapor, a time crystal's uniqueness is not in its spatial arrangement, but in its behavior through time. Imagine a perfectly frictionless clock that ticks forever, not because it is wound up, but as its fundamental ground state of existence. It breaks a sacred symmetry of physics, the assumption that the laws of nature look the same at every moment in time. For a time crystal, the lowest energy state is not a still and quiet one. It is a state of perpetual periodic motion. The atoms within it are locked in a dance that repeats not because they are pushed, but because it is their most restful, natural condition. This was once thought to be as impossible as a perpetual motion machine, until Nobel laureate Frank Wilczek proposed the idea, and subsequent experiments brought it to life in controlled quantum systems. Scientists have created these crystals using chains of ions or clouds of atoms, nudging them just once to set their rhythm. Astonishingly, they continue to oscillate at a specific frequency, ticking like a quantum metronome long after the initial push has faded. This persistent rhythm, immune to disturbances and requiring no energy input, opens a revolutionary window into non-equilibrium physics, the study of systems that are driven and never settle into a quiet balance. The entire universe, from the turbulent hearts of stars to the explosive birth of galaxies, operates far from equilibrium. Time crystals offer a pristine laboratory to understand the hidden rules governing these dynamic, ever-changing states of cosmic matter. Their most immediate promise, however, lies in the heart of quantum computers. The fragile quantum bits or qubits that form the basis of these machines are notoriously delicate, easily losing their coherence from the slightest environmental whisper. A time crystal, with its robust, self-correcting rhythm, could act as a perfect quantum memory, a stable backbone that protects information from decay. It could orchestrate the operations within a quantum processor, ensuring calculations proceed with a fidelity that today seems like a dream. Beyond our laboratories, could such structures exist in the wild cosmos? Could the dense, spinning cores of neutron stars or the swirling plasma near event horizons host natural time crystals? They're atomic lattices ticking to the silent, perpetual drumbeat of the universe itself. They might be the most stable clocks in existence, cosmic timekeepers whose rhythms outlast the stars. String theory is not the only path toward unifying the cosmos. A rival vision, known as loop quantum gravity, proposes a radically different solution by reweaving the very fabric of spacetime. Instead of imagining tiny, vibrating strings, this theory suggests that space itself is not smooth and continuous, but is woven from an unimaginably dense fabric of finite, woven loops. Picture the universe as a cosmic tapestry, where each individual thread is a tiny, one-dimensional loop of gravitational field. These loops link together to form the net of space, and the geometry of the universe emerges from their connections. This quantum of space is the smallest possible unit, a single pixel in the grand canvas of reality. There is no such thing as a distance smaller than this, no before the Big Bang in the classical sense, because time and space themselves are quantized. This discrete structure of spacetime provides a natural shield against the terrifying infinities of the classical gravitational collapse. In Einstein's general relativity, the Big Bang is a singularity, a point of infinite density where the laws of physics break down completely. But in the loop quantum cosmos, gravity becomes repulsive at these extreme densities, acting as a cosmic trampoline. The collapse of a previous universe would not end in a meaningless singularity. Instead, the repulsive quantum force would halt the collapse and trigger a new expansion. This is the big bounce. Our universe may not have been born from nothing, but could be the rebirth of a previous cosmos that contracted into an ultra-dense state before springing back into a new cycle of creation. The implications are profound. The universe could be eternally cyclic, with no true beginning and no final end, a perpetual cycle of contraction and expansion. This offers a beautiful resolution to the question of what came before the Big Bang. There was no before in a linear sense, only an endless, cyclical transformation where each universe bequeaths a quantum imprint to its successor. The cosmos becomes an eternal phoenix, forever dying in a fire of immense density, only to be born again from its own ashes. The same equations that predict the absolute darkness of a black hole also suggest the existence of its luminous opposite. A white hole is a region of spacetime where nothing can ever enter, a cosmic fountain that only pours out. While matter and energy can explode from its core, the gravitational pull at its boundary is so immense that nothing, not even light, can cross inward. It is the ultimate one-way street, an exit door from the universe with no handle on the outside. If you were to approach one, you would witness a blinding torrent of radiation and particles erupting from a single point, but you could never reach the source. The white hole is not just a different kind of object, it is a black hole's life story played in reverse, a mathematical echo of a collapse running backward in time. This bizarre symmetry leads directly to one of the most fantastic ideas in all of physics. An Einstein-Rosen bridge, better known as a wormhole, could be the tunnel that connects a black hole to a white hole. Imagine the universe as a vast, flat sheet of paper. A wormhole would be like a fold that brings two distant points together, with a shortcut tunnel bridging the gap between them. The black hole would be the irresistible entrance, the throat of the wormhole the passageway, and the white hole the exit in another location, or perhaps in another universe entirely. This is not mere science fiction, but a valid, though highly unstable, solution to Einstein's field equations. The moment any matter, even a single photon, tried to travel through this cosmic shortcut, the tunnel would collapse faster than the speed of light, pinching off into a singularity and crushing anything inside. To hold a wormhole open, you would need a form of matter with negative energy density, a substance that gravitationally repels rather than attracts. This exotic matter is purely theoretical, but its potential is staggering. A stable, traversable wormhole would be the ultimate time machine. According to relativity, the two mouths of the wormhole could experience time at different rates. If you moved one mouth at near light speed and then brought it back, it would have aged less than the stationary mouth. Walking through the tunnel would not just be a journey across space, but a leap into the past of the other side. You could potentially step out billions of years into the past of a distant galaxy, witnessing cosmic history unfold. The white hole itself might be the other end of this incredible journey, a fountain of matter that is not being created but being delivered from a different point in spacetime. Despite their mathematical elegance, no evidence for white holes or wormholes has ever been found. They may be impossible artifacts of the equations, beautiful mirages in the desert of theoretical physics. Yet they persist in our imagination and our calculations, a testament to a universe that continually offers pathways to the seemingly impossible, reminding us that every exit might also be an entrance to somewhere else entirely. Yet after 30 cosmic mysteries, one question towers above all others. Is there a single, ultimate theory, a final equation that can explain everything from the dance of quarks to the whirl of galaxies? This is the dream of a theory of everything, a framework so complete it would unify all of physics into one elegant and profound statement. For centuries, our understanding has been fragmented. We have general relativity, which masterfully describes the force of gravity and the large-scale structure of spacetime. And we have quantum mechanics, which perfectly predicts the behavior of the subatomic world. The problem is that these two pillars of modern physics are fundamentally incompatible. Their mathematical languages clash, and when their domains overlap, such as at the center of a black hole or the moment of the Big Bang, the result is nonsense, a storm of infinite values where physics breaks down completely. A successful theory of everything would weave these two contradictory masterpieces into a single, coherent tapestry, revealing the hidden pattern connecting the vast and the minute. The quest for this unification has been guided by a powerful, almost spiritual principle in physics, the pursuit of beauty and symmetry. Time and again, the universe has shown us that its deepest laws are not messy or arbitrary, but are expressed through exquisite mathematical symmetries. Think of a perfectly shaped snowflake. It looks the same when you rotate it by 60 degrees. This is a simple symmetry. The fundamental laws of the universe possess far more profound and abstract symmetries, governing the relationships between forces and particles. Physicists like Einstein were driven by a faith that the final theory must be simple, elegant, and beautiful in its mathematical form. This is not just an aesthetic preference, it is a proven guide. The standard model of particle physics, which describes 3 of the 4 fundamental forces, was largely constructed by following the trail of mathematical symmetry. The challenge, however, is immense. The leading candidates, string theory and loop quantum gravity, are both breathtakingly beautiful in their own ways, but they remain untested. String theory proposes a universe of vibrating strings, while loop quantum gravity suggests spacetime is woven from tiny, discrete loops. Both are mathematically formidable, requiring a level of abstraction that is difficult to connect to any experiment we can currently perform. This is the great dilemma. How do we test a theory that operates at energies 1 trillion times greater than our most powerful particle colliders can produce? A true theory of everything would be more than just a scientific triumph. It would be a philosophical revolution. It would answer the ancient question of why the universe is the way it is. It could explain the origin of the cosmic constants, those seemingly arbitrary numbers that define the strength of gravity and the mass of an electron. Were they the only possible values, or are they the outcome of a deeper, more fundamental law? Such a theory could tell us if our universe is unique, or just one possibility in an infinite multiversal landscape. It would reveal the ultimate nature of reality, showing us whether we live in a cosmos of strings, loops, or something beyond our current imagination. To hold such an equation would be to hold the blueprint of existence, a cipher that finally decodes the universe's most hidden and beautiful patterns. We have traveled from the holographic edges of reality to the silent, dark heart of the cosmos, exploring 30 different keys to the universe's greatest mysteries. Each theory, from the quantum branching of many worlds to the cosmic censorship of the zoo hypothesis, offers a unique lens, a different way of seeing the hidden patterns woven into everything from the fabric of space-time to the nature of consciousness itself. These are not just abstract ideas, they are profound invitations to rethink what is real. They challenge us to see the universe not as a static stage, but as a dynamic, evolving, and deeply strange tapestry where black holes might be gateways, reality might be a simulation, and our own existence could be a statistical miracle in an infinite multiverse. The journey reveals that the cosmos is far grander, more mysterious, and more interconnected than we ever dared to believe. So which of these cosmic keys resonates most deeply with you? Was it the eternal cycles of the Big Bounce, the haunting silence of the Great Filter, or the elegant vibrations of string theory? Share your favorite mind-bending theory in the comments below. And if you are hungry for more journeys to the edge of understanding, subscribe for our next deep dive into the mysteries of space.